The first predators, how ancient oceans became a battlefield. The history of life on Earth is often told as a story of progress, a ladder climbing from simple cells to complex intelligence. But there is a darker, more visceral engine driving this ascent, a force that has shaped the anatomy and behavior of nearly every creature that has ever lived. That force is predation. Today, the ocean is a dangerous place, filled with sharks, orcas, and barracudas, but it was not always so. For billions of years, the oceans were silent and largely peaceful. The transformation of the marine environment from a passive garden into a chaotic battlefield is one of the most significant events in the history of our planet. It is the story of the first predators, the creatures that invented the act of killing, and how they forced the rest of life to adapt or perish. This narrative spans hundreds of millions of years, from the nebulous mists of the Proterozoic to the armored clash of the Devonian, marking the rise of the hunter and the eternal arms race that followed. The silence before the storm. To understand the magnitude of the arrival of predators, one must first understand the world that preceded them. If we were to travel back in time approximately 600 million years to the Ediacaran period, we would find an alien world. The oceans were filled with life, but it was life unlike anything seen today. The water was thick, with microbial mats, sticky carpets of bacteria that coated the seafloor. Upon these mats lived the Ediacaran biota, a mysterious assemblage of soft-bodied organisms. Creatures like Dickinsonia, flat and segmented like a quilted air mattress, lay motionless on the sediment. Others, like Charnia, resembled fronds or feathers anchored to the seafloor and swaying gently in the currents. This was the Garden of Ediacara. In this epoch, there were no jaws, no teeth, no claws, and no eyes. Animals did not need to see because nothing was coming to eat them. They did not need to hide, and they did not need armor. The primary mode of existence was osmotrophy, the passive absorption of nutrients from the water or the underlying bacterial mats. It was a slow, energy-low existence. There was no fear in the Ediacaran Ocean because the concept of an enemy did not yet exist. Energy flowed through the ecosystem in a slow trickle, recycling through decay and absorption. But this tranquility was structurally unstable. Evolution is an opportunist, and a vast reservoir of energy stored in the bodies of these soft creatures was waiting for an organism bold enough to seize it. The first bite, the end of the Ediacaran and the dawn of the Cambrian period, roughly 541 million years ago, marks the most dramatic turning point in the biological history of Earth. This transition is often associated with the, quote, Cambrian explosion, a rapid diversification of life forms. While many factors contributed to this explosion, including rising oxygen levels and changes in ocean chemistry, the rise of predation was the spark that ignited the powder keg. The evidence for the first predators is subtle, but undeniable. It begins not with a fossil of a monster, but with a fossil of a victim. In the late Ediacaran rocks, paleontologists found the shells of a small, tube-dwelling organism called Claudina. These tiny, cone-like creatures built mineralized skeletons, one of the first animals to do so. But what makes Claudina famous is what happened to it. Many Claudina fossils bear round, perfectly bored holes. These holes are not accidental fractures. They are the work of a predator, an organism that used an acid or a mechanical drill to breach the shell and consume the soft animal inside. This is the first concrete evidence of carnivory in the fossil record. The Garden of Ediacara was ending. Someone had learned how to break in. The invention of biomineralization, the ability to create hard shells from calcium, carbonate, or phosphate, was likely a direct response to this new threat. As predators began to nip and tear at soft bodies, natural selection heavily favored those with harder exteriors. The arms race had begun. The soft, quilted organisms of the Ediacaran vanished, replaced by a new fauna that was armed and dangerous. The Cambrian explosion and the invention of the eye. As the Cambrian period began, the pace of evolution shifted from a crawl to a sprint. The development of complex nervous systems and, crucially, vision transformed the battlefield. Before the Cambrian, the ocean was a world of touch and chemical gradients. A predator had to stumble upon its prey. But with the evolution of the eye, a predator could identify a target from a distance. This fundamentally changed the spatial dynamics of the ocean. No longer could a creature simply sit on the seafloor and hope to be ignored. The evolution of the compound eye was a game changer. Arthropods, the group that includes modern insects, crustaceans, and spiders, were the pioneers of this technology. With segmented legs, hard exoskeletons, and multifaceted eyes, they were the tanks and fighter jets of the Cambrian seas. The fossil deposits of the Burgess Shale in Canada and the Maoshinshan shales in China have revealed these creatures in exquisite detail, freezing the moment when the ecosystem organized itself into complex food webs. The tyrant of the Cambrian. Dominating this new dangerous world was the first true super predator, Anomalocaris. The name means abnormal shrimp, a moniker given because its disparate body parts were originally discovered separately and thought to be different animals. Its mouth was mistaken for a jellyfish, its grasping appendages for shrimp tails, and its body for a sea cucumber. When the pieces were finally assembled, they revealed a creature that was terrifying by the standards of the time. Anomalocaris was a giant among dwarves. While most Cambrian animals were a few inches long, Anomalocaris could grow up to a meter or more in length. It swam with undulating flaps running down the sides of its body, propelling it through the water with a grace that belied its deadly intent. Its head was equipped with two large, stalked compound eyes, offering it excellent vision. Beneath the head were two spiny, curling appendages used to snag prey and bring it toward a square, tooth-lined mouth that acted like a biological nutcracker. Biomechanics studies suggest that Anomalocaris was not a cruncher of hard shells, as originally thought, but a predator of soft to medium-bodied animals. It likely cruised the water column, snatching up swimming arthropods or worms. Its presence fundamentally altered the behavior of marine life. For the first time, death could come swiftly from above. The existence of such a large predator implies a complex ecosystem beneath it to support its metabolic needs. Anomalocaris sat at the apex of a trophic pyramid that was rapidly becoming more vertical and complex. The prey strikes back. In response to the rise of predators like Anomalocaris and other grasping arthropods, prey species evolved elaborate defenses. This is the core principle of the suggests that organisms must constantly adapt, evolve, and proliferate, not merely to gain reproductive advantage, but simply to survive, while pitted against ever-evolving opposing organisms. The trilobites are the most iconic example of this defensive adaptation. These arthropods, resembling woodlice or horseshoe crabs, dominated the seafloor for hundreds of millions of years. Their dorsal side was covered in a tough, calcified exoskeleton, providing a shield against attack. But armor was not their only defense. Many trilobites evolved the ability to annulment, curling up into a tight ball to protect their soft underbelly, much like a modern pill bug or armadillo. This behavior is preserved in the fossil record, with many trilobites found fossilized in this defensive posture, likely buried by a sudden mudslide while trying to protect themselves. Other creatures took different routes. Hallucigenia, a velvet worm relative that looked like a hallucinations brought to life, sported long, rigid spikes along its back. Any predator attempting to swallow it would be met with a mouthful of quills. Wiwaxia, a slug-like creature, covered itself in scale-like sclerites and long sword-like spines. The visual landscape of the Cambrian Ocean was defined by spikes, shells, and plates. It was a visual language that said, "Do not eat me, it will hurt." The arsenal of the Burgess Shale. The Burgess Shale reveals that Anomalocaris was not alone. The Cambrian oceans were filled with a variety of predators, each trying to solve the problem of how to catch and eat other animals. Opabenia was a smaller, stranger cousin of Anomalocaris. It possessed 5 eyes on stalks and a long, flexible nozzle with a claw at the end, resembling a vacuum cleaner hose. This proboscis was likely used to reach into burrows or crevices to extract hiding prey. Herdiids, relatives of Anomalocaris, evolved large, shield-like carapaces on their heads. While the function of these shields is debated, they may have been used to plow through sediment or entrap prey. The diversity of predatory appendages in the Cambrian is staggering. Evolution was experimenting with every possible configuration of grasping claws, filtering combs, and crushing mandibles. One crucial development during this time was the agronomic revolution. As predators prowled the water and the surface of the sediment, prey animals began to dig. Before the Cambrian, the seafloor was relatively undisturbed. Now, worms and arthropods burrowed deep into the mud to escape detection. This bioturbation changed the chemistry of the oceans, oxygenating the sediment and opening up new ecological niches. Predators, in turn, had to evolve ways to dig them out. The battlefield extended from the water column down into the earth itself. The Ordovician radiations and the rise of the cephalopods. The Cambrian period ended with a series of extinctions, but the predator-prey dynamic did not stop. It accelerated. The following period, the Ordovician, saw the Great Ordovician Biodiversification Event. Life exploded in diversity, filling the niches created during the Cambrian. In this era, a new group of predators rose to challenge the arthropods, the cephalopods. Today, cephalopods are represented by octopuses, squids, and cuttlefish. In the Ordovician, they were the nautiloids. Unlike the soft-bodied octopuses of today, these ancient cephalopods lived inside hard, conical shells. They invented a method of locomotion that gave them a distinct tactical advantage: jet propulsion. By forcing water out of a siphon, they could dart through the water with speed and agility that the undulating swimmers of the Cambrian could not match. The apex predator of the Ordovician was Camaraoceras, a giant orthicone, straight-shelled nautiloid. Estimates of its size vary, but it may have reached lengths of 6 meters or more. Imagine a creature resembling a giant squid, stuffed inside a long, straight ice cream cone shell, trawling the ancient reefs. Its tentacles would have seized trilobites and sea scorpions, dragging them toward a sharp, parrot-like beak, capable of crushing armor. The rise of the cephalopods marked a shift in the intelligence of predators. Cephalopods possess complex brains and sensory systems. They likely employed stealth and ambush tactics, using their tentacles to manipulate prey. The trilobites, facing this new threat, responded by evolving even thicker armor and more complex eyes. Some trilobites developed eyes on stalks to see above the mud. Others evolved wraparound vision to detect motion from any angle. The Silurian and the sea scorpions. As geological time rolled into the Silurian period, roughly 443 million years ago, the arthropods launched a counteroffensive in the war for dominance. The Eurypterids, commonly known as sea scorpions, grew to terrifying proportions. These were not true scorpions, but cousins to arachnids and horseshoe crabs. The most famous of these, Pterygotus, was one of the largest arthropods to ever live, reaching lengths of over 2 meters. Unlike the bottom-crawling Cambrian arthropods, Pterygotus was an active swimmer. It had paddle-like rear legs that acted as hydrofoils, allowing it to chase down prey. Its front appendages were modified into massive pincers, armed with teeth, which it used to grab and crush. The eurypterids dominated the shallow, brackish waters and the burgeoning coral reefs. They represent the pinnacle of the arthropod body plan applied to predation. However, they suffered from a fundamental limitation, the physics of the exoskeleton. An animal with an external skeleton must molt to grow. During the molting process, the animal is soft and vulnerable. Furthermore, as size increases, the weight of the exoskeleton becomes prohibitive, and the respiratory systems of arthropods struggle to supply oxygen to massive tissues. While they ruled the Silurian, their reign was destined to be challenged by a new biological architecture, the internal skeleton. The vertebrate revolution. While the invertebrates, arthropods, and mollusks were battling for supremacy, a quiet revolution was occurring in the shadows. The chordates, the group that includes humans, had been present since the Cambrian as small, eel-like creatures like Pikaia. For millions of years, they were insignificant, bottom feeders, likely prey for the larger invertebrates. But they possessed a secret weapon. The notochord, a flexible rod supporting the body, which would eventually evolve into the vertebral column. During the Silurian and into the Devonian period, early vertebrates began to diversify. The first fish were jawless, known as agnathans. They resembled armored tadpoles or hagfish, sucking up mud or rasping at algae. They were heavily armored with bony plates, a defense against the eurypterids and cephalopods. But evolution was about to provide them with the ultimate weapon, the jaw. The origin of jaws. The evolution of the jaw is perhaps the most significant event in vertebrate history. It transformed fish from passive scavengers into active hunters. The leading scientific theory, derived from comparative anatomy and embryology, suggests that jaws evolved from the gill arches of jawless fish. These bony arches originally supported the gills, helping the fish to breathe. Over time, the first pair of arches moved forward and enlarged, initially to help pump water over the gills for more efficient respiration. Eventually, this pumping mechanism became a grasping mechanism, with the addition of teeth, which likely evolved from modified skin scales. The vertebrate jaw became a killing tool. This allowed fish to seize prey, bite chunks out of larger animals, and process food more efficiently. The digestive advantages were immense. An animal that can chew or tear its food can digest it faster and extract more energy, fueling a higher metabolism and more active lifestyle. The age of fishes and the placoderms. The Devonian period, starting around 419 million years ago, is known as the Age of Fishes. It was here that the jawed vertebrates exploded in diversity and size, effectively ending the reign of the invertebrates. The most formidable of these early jawed fish were the placoderms. Placoderms were the tanks of the Devonian seas. They were covered in thick, interlocking bony plates that protected their heads and thorax. Unlike modern fish, their teeth were not separate structures rooted in the jaw. Rather, the bones of the jaw themselves were sharpened into self-sharpening cutting edges. The king of the placoderms, and arguably the first vertebrate superpredator, was Dunkleosteus. Growing up to 6 meters long and weighing over a ton, Dunkleosteus was a monster. Its head was encased in heavy armor. Its jaws functioned like a high-powered guillotine. Biomechanical analysis of the leverage in Dunkleosteus's skull suggests it delivered one of the most powerful bites in animal history, rivaling that of T-Rex and the great white shark. Dunkleosteus was not just a biter, it was a suction feeder. By rapidly opening its massive jaws, it created a vacuum that sucked prey into its mouth in milliseconds. This allowed it to catch fast-swimming prey or drag reclusive animals out of crevices. Fossilized regurgitated remains found in association with Dunkleosteus fossils show that they ate everything: sharks, other placoderms, and invertebrates. The hunter had become the ultimate consumer. The rise of the placoderms forced a change in the ocean's defense strategies. Armor was still useful, but speed and maneuverability were becoming increasingly important. The heavy armor of the placoderms made them formidable but energetically expensive to maintain and heavy to swim with. The rise of the sharks. While Dunkleosteus ruled the top of the food chain, another group of jawed fish was evolving a different strategy. These were the chondrichthyans, the cartilaginous fish, ancestors of modern sharks and rays. One of the best-known early sharks was Cladocellaceae. Compared to the lumbering, armored Dunkleosteus, Cladocellaceae was a Ferrari. It shed the heavy, bony armor of its ancestors and competitors, opting instead for a skeleton made of lightweight, flexible cartilage and skin covered in tiny, drag-reducing scales called dermal denticles. This made Cladocellaceae fast and agile. It possessed a streamlined, torpedo-shaped body and a high aspect ratio tail fin, optimized for high-speed pursuit. Cladocellaceae represented a shift toward efficiency. It didn't need to be a tank if it could outswim the tank. It didn't need armor if it didn't get caught. These early sharks were visual hunters, with large eyes and likely keen olfactory senses. They patrolled the Devonian oceans, snapping up smaller fish and squid. While they were not yet the apex predators, Dunkleosteus still held that title. The shark body plan proved to be more durable in the long run. When the Devonian ended with a mass extinction, the heavy placoderms vanished, but the agile sharks survived, setting the stage for their future dominance. The move to land, a predator's push. It is worth noting that the intensity of predation in the Devonian oceans may have influenced one of the most important events in our own history, the colonization of land. The water was crowded, dangerous, and filled with hungry mouths. The margins of the continents, the shallow tidal flats and river deltas, offered a refuge. Fish like Tiktaalik, which possessed limb-like fins and lungs, occupied these shallow interfaces. While the drive to move onto land was complex, involving food availability and environmental changes, the pressure of predation in the deeper waters cannot be ignored. By moving into the shallows, these early tetrapods escaped the giant placoderms and sharks. In a way, the ferocity of the marine battlefield pushed our ancestors onto the beach. The Red Queen and the evolutionary engine. The story of these first predators serves as a perfect illustration of the Red Queen hypothesis. Named after the character in Lewis Carroll's Through the Looking Glass who tells Alice it takes all the running you can do to keep in the same place, this hypothesis explains the constant evolutionary arms race. When a predator evolves a better weapon, like the eye or the jaw, the prey must evolve a better defense, like armor or speed, just to survive. This adaptation by the prey then puts pressure on the predator to improve further. This feedback loop drives complexity. It is no coincidence that the explosion of animal diversity coincides with the rise of predation. Predation acts as a quality control mechanism for the ecosystem. It removes the sick, the slow, and the genetically less fit, ensuring that the breeding population retains the most advantageous traits. It also facilitates energy flow. Predators are the engines that move energy from the bottom of the food web to the top. The existence of a complex, multi-tiered food web is a hallmark of a healthy, mature ecosystem. The legacy of these ancient battles is written in the anatomy of every modern animal. The human eye is a descendant of the optical systems that were honed to spot predators in the Cambrian. Our spine is the legacy of the early fish that needed a stiff rod to leverage their muscles for swimming away from eurypterids. Our adrenaline response, the fight or flight mechanism, is a biological echo of the terror felt by a trilobite when a shadow passed overhead. Specific battlefields, the Lagerstätten. Our knowledge of these ancient battlefields comes from specific geological sites known as Lagerstätten, places of exceptional fossil preservation. To understand the nuance of these eras, we must look at the specific sites that gave us the data. The Burgess Shale in British Columbia is the most famous. Discovered by Charles Walcott in 1909, it preserved the soft tissues of Cambrian animals. Before this discovery, we only knew of shelled creatures. The Burgess Shale revealed the soft, grasping limbs of Anomalocaris and the delicate, lace-like gills of Morella. It showed us that the weird wonders of the Cambrian were not failed experiments, but highly specialized creatures adapted to their specific environments. Similarly, the Chengjiang biota in China gives us a window into the early Cambrian, slightly older than the Burgess Shale. Here we see the very first fish, Milocunmingia, swimming amidst the chaos of giant arthropods. We see the sophisticated neural architecture of these early animals, proving that the brain was a priority evolution from the start. The Gogo Formation in Australia offers a 3D look at the Devonian. While most fossils are flattened like roadkill, the Gogo fossils are preserved in limestone nodules. When dissolved in acid, the bones of placoderms emerge in perfect three-dimensional shape. This allowed scientists to reconstruct the jaw muscles of Dunkleosteus and understand the mechanics of the first true bite. It also revealed that placoderms gave birth to live young, adding another layer of complexity to their reproductive strategies. The mechanics of the kill. As we analyze the rise of predators, we must look at the mechanics of the kill. Predation is, at its core, a transfer of energy, but catching prey costs energy. A predator must calculate, evolutionarily speaking, whether the energy gained from a meal exceeds the energy spent catching it. This thermodynamic equation dictated the forms of the first predators. Anomalocaris was a cruiser. It likely spent long periods gliding, using little energy until it spotted prey. Its large size gave it thermal inertia and a longer reach. The Eurypterids were ambush predators. They sat and waited, an energy-efficient strategy that relied on explosive power. Active hunters, like the early sharks and placoderms, required high metabolic rates. This need for oxygen and fuel drove the evolution of better gills and more efficient circulatory systems. The heart of a vertebrate is a pump designed to service the high-performance engine required for predation. The separation of oxygenated and deoxygenated blood, which reached its peak in mammals and birds, began its long evolutionary journey in the demands of the Paleozoic hunter, sensory warfare. The battlefield was not just physical, it was sensory. The Cambrian introduced sight, but subsequent eras refined other senses. The lateral line system in fish is a series of fluid-filled canals along the side of the body that detect pressure changes in water. This allowed fish to feel prey, moving in the dark or behind them. It was a crucial adaptation for predators hunting in murky water or at night. Chemoreception, smell and taste, became incredibly sophisticated. The lobes of the brain dedicated to processing smells enlarged in early fish. A shark can detect a drop of blood in an Olympic-sized swimming pool. The roots of this ability lie in the Devonian need to find wounded prey before a competitor did. The prey, in turn, developed sensory countermeasures. Some animals evolved to be chemically invisible, masking their scent. Others, like certain cephalopods, developed camouflage, changing their skin color and texture to blend in with the background. While we associate this dynamic color change with modern octopuses, the basic biological machinery was being laid down in the ancestors of these groups. The end of the ancient order. The era of the first predators, from the Cambrian to the end of the Devonian, established the rules of engagement that still govern the ocean today. However, the specific players changed. The end of the Devonian was marked by a mass extinction that wiped out the placoderms. Dunkleosteus and its kin vanished. The Eurypterids slowly declined, eventually disappearing in the Permian. Why did the placoderms fail? They were the supreme rulers of their age. It is possible that their overspecialization was their downfall. They were heavily invested in armor and massive size. When the environment changed, perhaps due to ocean anoxia or cooling, they could not adapt fast enough. The sharks, with their generalized body plan and diverse diet, survived. This is a recurring theme in the history of predators. The biggest and most specialized often fall the hardest during extinctions, while the smaller, more adaptable generalists survive to inherit the Earth. The Carboniferous and Permian periods that followed saw the rise of new predators, including the chimera-like cartilaginous fish and eventually the marine reptiles of the Mesozoic. But these later monsters were building on the foundations laid by the pioneers. The ichthyosaur looked like a dolphin, but it chased prey using jaws and teeth invented by Devonian fish, using eyes invented by Cambrian arthropods. Reflections on the battlefield. Looking back at the ancient oceans, it is easy to project human emotions onto these creatures, to see the predator as cruel and the prey as innocent. But nature makes no such distinctions. Predation is simply a strategy, a way of existing. The cruelty of the Anomalocaris or the Dunkleosteus was the engine of creation. Without the pressure they exerted, life might have remained a carpet of slime on the sea floor. The fear of being eaten forced life to become faster, smarter, and more complex. It forced the development of the shell, the spine, the eye, and the brain. We are the product of survivors. Every one of our ancestors, stretching back to the worm-like chordates of the Cambrian, managed to avoid being eaten long enough to reproduce. We carry the legacy of that evasion in our very DNA. The Garden of Ediacara was a paradise lost, a time of peace that could not last. But the battlefield of the Phanerozoic, the eon of visible life, gave us the diversity and vibrancy of the living world. The first predators broke the silence of the oceans, and in doing so, they woke the world up. The interplay between the hunter and the hunted continues today. In the deep ocean, sperm whales battle giant squids, echoing the clashes of orthocones and sea scorpions. On the reefs, sharks patrol just as their ancestors did 400 million years ago. The actors have changed, but the play remains the same. It is a drama of energy, adaptation, and survival, a story that began with a single bite in a Precambrian sea. Understanding this history gives us a profound perspective on the fragility and resilience of life. Ecosystems are built on a delicate balance of terror and abundance. Removing the top predators, as humans have done in many modern ecosystems, can lead to a collapse of the structure, just as the extinction of placoderms reshaped the Devonian seas. The ancient oceans teach us that predators are not just killers. They are the shepherds of biodiversity, the architects of the biological world. As we study the fossils of Claudina with its drilled hole, or the serrated jaws of Dunkleosteus, we are looking at the moments where the rules of life were written. These were the first predators, the bringers of death, and paradoxically, the drivers of life. They turned the ocean into a battlefield, and in the chaos of that war, the infinite forms of nature were forged. The geological context of predation. To fully appreciate the rise of these predators, one must also consider the stage upon which they played, the shifting continents, and the changing chemistry of the oceans. During the Cambrian, the continents were dispersed, creating vast areas of shallow, sunlit continental shelves. These were the perfect incubators for life. The abundance of light allowed for the proliferation of algae and phytoplankton, the base of the food web. Without this rich primary production, the high-energy lifestyles of predators like Anomalocaris would have been impossible. By the time of the Devonian, the continents were moving toward the configuration that would eventually become Pangaea. The formation of massive reef complexes, arguably the largest in Earth's history, provided a complex three-dimensional environment. Predation is different in a reef than in the open ocean. In a reef, there are hiding spots, corners, and shadows. This complexity drove the evolution of maneuverability. The pectoral fins of fish evolved not just for steering, but for braking, turning in place, and hovering. The placoderms and early bony fish had to navigate dense forests of coral and sponge, hunting prey that knew the terrain. Oxygen was the other critical factor. Predation is aerobic. It consumes vast amounts of oxygen. The pulses of oxygenation in the atmosphere and oceans correspond roughly with the leaps in predator size and complexity. You cannot have a giant active predator in an oxygen-poor ocean. The interaction between the biosphere, life, and the geosphere, the Earth, is tight. The burrowing of worms released nutrients. The photosynthesis of algae released oxygen. The predators consumed the worms and the algae eaters, driving the cycle faster. The psychological landscape of the deep time. While we cannot know the mind of a trilobite or a placoderm, we can infer the behavioral changes that predation caused. This is the concept of the landscape of fear. In an ecosystem with predators, prey animals do not forage randomly. They avoid open areas. They feed at times when predators are less active. They congregate in herds or schools. The schooling behavior of fish, which we take for granted, likely evolved as a defense against the predators of the Paleozoic. A school confuses a predator, making it difficult to target a single individual. It is a sensory overload defense. The many eyes hypothesis suggests that in a group, there is a higher chance of spotting a predator early. This social behavior, the roots of cooperation, was driven by the threat of annihilation. Even the migration patterns of marine animals may have deep roots in these ancient times. Moving to shallow waters to breed, or moving to deep waters to hide during the day, diel vertical migration, are strategies to mitigate risk. The daily rhythm of the ocean, the massive movement of biomass up and down the water column, is a dance choreographed by the presence of predators, the fossil record's bias. A caveat in our understanding of the first predators is the bias of the fossil record. We know Dunkleosteus because it had hard bony plates. We know Anomalocaris because of the miraculous preservation of the Burgess Shale. But what about the soft-bodied predators that didn't leave a trace? There were likely jellyfish-like predators, giant predatory worms, and other nightmares that rotted away completely. Our view of the ancient battlefield is like looking at a war through a keyhole. We see the tanks, placoderms, and the soldiers with helmets, trilobites, but we might miss the spies and the assassins. However, the functional morphology of the survivors helps us fill in the gaps. The defenses of the prey tell us about the weapons of the predators we cannot see. If a fossil clam has a thick shell, we know something was trying to crush it, even if we never find the crusher. The inevitability of predation. Was the rise of predation inevitable? Astrobiologists ask this question when considering life on other planets. If we find life on Europa or Enceladus, will there be predators? The consensus is likely yes. Energy gradients exist to be exploited. If an organism accumulates energy, biomass, another organism will eventually find a way to steal that energy, rather than synthesizing it from scratch. It is a thermodynamic shortcut. Therefore, the story of Earth's first predators is likely a universal story. Anywhere life reaches a certain level of complexity and density, the hunter will emerge. The garden phase is temporary. The battlefield phase is the stable state of complex life. Conclusion: the eternal war. The journey from the peaceful mats of the Ediacaran to the shark-infested waters of the Devonian covers nearly 200 million years of history. It was a time of radical experimentation. Nature tried every shape, every strategy, and every weapon. Many failed. The five-eyed Apabinia has no living descendants. The giant Eurypterids are gone. The armor-plated placoderms are dust. But the legacy of their struggle remains. The invention of the predator-prey dynamic was the catalyst that transformed the Earth from a static microbial world into a dynamic multicellular one. It forced life to get bigger, faster, stronger, and smarter. The ocean is no longer the silent world of the Proterozoic. It is a cacophony of clicks, whistles, grunts, and the silent pressure waves of hunting fish. It is a world of color, movement, and intelligence. All of this complexity was bought with the blood of the fallen in the ancient seas. The first predators were the architects of the modern world, carving the shape of life with teeth and claws. As we gaze into the blue depths of today's oceans, we are looking at the continued unfolding of a drama that began 500 million years ago. The endless, driving, creative force of the hunger for life. The battlefield has never closed. It has only grown more complex. And in that complexity lies the beauty of the natural world.